Welcome to our lectures on NPTEL courses on the power quality improvement technique. Today will be our third class on the PWM voltage source converter, PWM technique for the voltage source converter. We shall start where we have finished in our previous class, that was the space vector modulations. So, we will just take our recapitulation, we have discussed this thing. So, this is a VDC and upper 3 switches will be named 1, 3, 5 and lower 3 switches will be named 2, 4, 6. So, that to maintain the difference of 3. Anyway, that is the same thing what we does in case of the full control converter T1, T3, T5 and T4, T6, T2. Same thing will be used here. And here formation of the voltage vector, we have seen that how to represent the 3 phase into the r theta coordinate. First from 3 phase we shall take it to the alpha beta frame, and from alpha beta frame we shall go back to the r theta coordinate. So, from the definition of the space vector, it is V, that will be called 2 by 3. A gives you 120 degree phase shift and this A square gives you 240 degree phase shift. So, we have discussed these things, why this neutral voltage will not arise when you have shorted. So, now we shall go to the next. So, that is the voltage of this is given by 2/3 VA VB, VA and VB will be multiplied with the A to make it a 120 degree phase shifted, and VC will be multiplied by A square to get aligned with that particular vector. Now, you can say that VA 2/3, that is we can go back to, that is VAN equal to V capital AN into ANN. So, we can rewrite like this. So, VAN plus VBN plus VCN and corresponding multiplication of the A and the A square plus NN 1 plus A plus A square, ultimately this summation generally gives you the 0. So, thus it will be 0 and thus you are just left with this part of this part of the value, and thus what we can say that VAN will be generated solely when you have VSA into VDC. So, similarly VAN will be equal to VDC into SB, and thus VAN equal to, we have VDC into SA, SB, SC, depending on whether it is 1 or 0. Thus, we can replace these values with VSA, SA into the switching state, that is A into SB, A square into SC. So, the switching logic comes into the picture. So, thus what you have, it is the only this value, thus it is 2/3 VD, VSA, ASB plus ASC. Now, this is the typical 2 level phase vector representations. First of all, if you want to have this vector is said to be A, that means that is in upper leg of A it is closed and it is open, and for the lower 2 leg this is open and this one is closed. Let us say this is the A and this is B and this is C. So, only what happened, this upper leg is closed and these 2 legs are closed. So, ultimately voltage will be VA, and this we will say that it is 101 or it is VA. You know that similarly a B phase will be lagging by 120 degree. So, for this reason what will happen, ultimately this switch will be closed and this switch will be open, and this switch and this switch will be closed, and for this reason you get the, this is basically your minus, this is basically your VB. Similarly, another 120 degree lagging, that is 240 degree, you will get your VC. So, you will have 0 1 0. So, from there you will start this convention. So, and generally we have chosen this convention something like this, and of course, you can rewrite this convention some other form also. Now, we will be splitting into the sectors. So, thus what happen, if it is VA, it should be minus VA. So, you can see that one correspondence to this switch, you know, if once, if switch 1 you go back to this circuit, this is 1 and other lower switch are closed, definitely what we will get is a VAN. Similarly, others are followed. So, it will be minus B, it will be minus A, sorry, extremely sorry. Similarly, this one is B and this will be minus B, and this one will be C and this one will be minus C. And thus, and it is been splitted into the 60 degree sectors. So, if by these summations, you know, VB is given by 2/3 of VD SA plus A SB plus A square SC, and from there we require to calculate what should be the value of the theta, and this magnitude, this radius is 2/3 of VDC, and of course, if you do the trigonometry, this is the perpendicular and this value will be 1 by root 3 of the VDC. Now, we require to generate the switching logic for this inverter, so that we can accurately generate those reference. Let us take the, it is in a first sector, and so the switching will be 1 0 0, that means in upper switch A leg is short and minus B and minus C is short, and in this case, you know, this is a 1 bit change, upper two upper legs are short and the C phase is short. Now, let us assume that this is the instantaneous voltage vector required to be generated and it is in sector 1. So, we can make like this by this for the this amount, if you apply the total voltage vector, that is 2/3 VDC, you will apply this much of this vector VA1, ultimately you have to match the area voltage curve. Similarly, let us consider for this will be applied for the T1 of the total voltage, and similarly if you, this will be applied for the time of T2, and task, we require to have a task of computing T1 and T2 rightly. That is the, that is something we require to do, and thus we can compute or generate this reference voltage. So, if T is the sample period of V1 is applied for the T1, then of course, you know, you have to apply, ultimately it is V1, T1 by T will be this amount of this value. Similarly, V2 is applied for the time T2 and ultimately V2 T2 by T will be this reference voltage vector. And if you have that, let us say it is switching at a 100 kilohertz, that means it is 100 microsecond, sorry, extremely sorry, it is 10 kilohertz, then it is 100 microsecond. In 100 microsecond, it may be some value, let us say 40 microsecond, it may be 30 microsecond, then total brings you to 17, then ultimately t will be rest 30 microseconds. So, this is the way difference, and generally this T 0 will be placed T by 2 0 and T by 2 0 at the beginning and at the end of the cycle. And since that since there is the combinations will start from 0 0 0 to 1 1 1. 1 1 1 or 0 0 0 are said to be the null vector when all the lower switches are closed, it is 0 0 0. So, voltage will be null. Same way if it is 1 1 1, voltage also will be null. We will see that how switching takes place in this case. So, as I told you that you are generating the clock pulses from DSP or FPGA, and for this reason the reference voltage sampled at a regular interval, that is t, with a sampling period of t ref, it is synthesized with the adjusting vectors and the 0 vectors. If t is a sampling period, V1 is applied for the time t1 and V2 is applied for the time t2, and 0 voltage is applied, as I told you, for the rest of the sampling period, that is equal to t in between this. So, we have to see the timing diagram of this. So, V reference is sampled and this duration may be t. So, what happened? This is the scale. What happened after some interval of time? Okay. This is I later mark at t 0. So, V A or S A B goes high and it will continue to be high. Thereafter, as I see that this is 1 0 0, thereafter 1 1 0, that means after a time interval t 1, this will go high, this V B, and thereafter what happens, since it start from 0 0 0, we want to have a 1 bit change. So, it will start from 0 0 0, thereafter it will go to 1 0 0, thereafter it will, since it is a 1 bit change, it will be 1 1 0, thereafter it should go to 1 1 1 to incorporate as a null vector. Since you have end here and again you start, so you should not start, this was the duration of t 1 and this was the duration of t 2. Since you start from 1 1 1, so next sequence will be 1 1 0 and that will be t 2. Thereafter, you will be 1 0 0, you will be again t 1, then again you come to this point. This is the cyclic order which you require to follow. Let us see here. So, that is what I was saying, that this duration will be t 1 equal to V 1 and this duration is t 2, and for the voltage V 2 will be high, V 1 V 2 both are high, and thereafter definitely this voltage vector is V 0 and that given by 0 0 0, that is a null vector where all the lower switches are closed, and that duration will be t by 2, and similarly at the end of it that duration will be again t by 2, you will get this value, and this is the way it will work. Now, what happened to this part of it? So, it will start from 1 1 1 and thus what happened, and you continue to till 1 till it becomes 0 0 0 here. After the interval of t 0 by 2, t 2 will be on. So, after this is t 2, thereafter what happened after t 1, so you have to back calculate it, and then it goes low and everything is goes low at this point. So, this will be comes here. So, this cycles this is called the cycle merging. This is the way this space vector modulation, 2 level space vector modulation works. So, now question is how to compute or calculate the value of these times T1, T2, T0 and the T7. Generally T0 and the T7 are having a same value, it is just put at the end or at the beginning of the switching cycle. So, if you do this voltage under curve, that is time integration of the voltage, that is necessarily flux. So, and you divide it by T, that it is the voltage only. So, 1 by T, where T is the reference switching sequence frequency, that is 0 to T, V ref dt, which you know that you require to inject the voltage at 35 volt at an angle of 45 degree. So, then what happen, generally if you have a 45 degree injection, of course T1 will be equal to T2, because V1 and V2 magnitude wise this voltage are equal. So, 1 by T 0 to T V dt plus V1 dt 0 to T1 plus 0 to T2 V2 dt plus 0 to T. Generally, you know what we can do, we can keep them same and multiply it by 2, that is also possible. So, ultimately if you can withdraw the integration sign from the both side, and thus what happen, V0 into T equal to V0 V reference into T equal to V0 into T0 plus V1 into T1 plus V2 into T2 plus V7 into T7. So, ultimately we require to see that this voltage vector is aligned to VA, but this is this and this magnitude is 1/3 of it 60 degree. So, you have to take the component of it to its direction. So, for this reason it is 2/3 Vd into T1 plus 2/3 Vd into cos 60, this angle is 60, thus it is cos 60 plus sin 60, and that magnitude will be your plus T7 into 0. So, this one is 0 and this one is also 0. So, what happen, you just reduce it, these terms, these null vectors. So, V reference into T will be equal to 2/3 Vd into T1 plus 2/3 Vd cos 30 plus j sin 30 into T2. So, what happened now, we can rewrite these equations where T1 plus T2 plus T0 or T7 equal to T, and we can rewrite this like this. So, this is the angle alpha, ultimately V ref equal to V ref cos alpha plus j sin alpha, you can equate them in alpha beta axis, and later if you rotate this by the synchronous frame, this alpha beta become DQ frame of reference. So, thus splitting in x and y axis, which is equivalent to the alpha and beta. So, we can write, that is V rev into T like this. So, equating the real and the imaginary part, we can write like this, you know, V rev cos alpha equal to 2/3 Vd into T1 plus 1/3 Vd into T2. Similarly, sin alpha T V rev sin alpha equal to 1/3 Vd into T2. This is the equation. From there you can calculate the time So, T1, T2 and T0 you can directly substitute, where M you can write it like this. So, M is Vref, what is the magnitude of it, the 40 degree, 40 volt, 30 volt, and VDC maybe 100 volt, whatever may be, and that reference is called the effective modulation index, and thus what happen, you can write it M, that is 3 by 2 T by root 3 cos alpha minus 1/3 T sin alpha. Similarly, we can calculate for the T2, T2 is just M into T sin alpha. So, thus we have calculated T1 and T2, subtract it from the total time T and get, and you divide it by 2 and that become T0 and T7. So, this is the way to calculate the times for the 2 level space vector modulation. Now, we require to now understand what is the benefit of it, or the comparisons of the sine triangle PWM with the space vector modulations. One aspect is that we just say one thing, that sine triangle PWM, that is the sine PWM, is simple to implement. We can implement this sine triangle PWM very easily. There is no computational burden every time we require to calculate this timing of the switching. So, that require a processors, and the digital programming is required in a digital domain. This complexity burden is more in case of this SBM, but with the arrival of the digital age and the first processors, it takes the gain over the accuracy, like exactly generating that particular THD what you require, and it is attuned to this vector control. So, for this reason, this space vector modulation has gaining much attention. And so, what are the other advantage? For m greater than 1, m equal to 1, I will come later, amplitude of the fundamental for VAO is VDC by 2, and amplitude of the line voltage is essentially root 3 by 2 VDC. So, what happened? We know that possible phase angle without over modulation is 1 by root 3 into VDC, and amplitude of line to line voltage can be up to VDC. Thus, straight away you can see that the line to line voltage in case of the space vector modulations is VDC minus root 3 by 2 VDC by root 3 by 2 VDC is a 15% increased in the utilizations of the in the line to line voltage for the output of the inverter, and thus we can transform into the better utilization of the DC bus voltage. So, this is the one opportunity of it, and generally what happen, you can do the same thing, you get this kind of thing in case of the third harmonic injection, but in third harmonic injection stress of the DC bus voltage were higher, but with a less DC bus voltage. That means less stress on your component, you can achieve 15% more the line voltage. For this reason, this method is preferred, even though it has got a computational complexity. So, we shall start, we not able to finish because just 2-3 minutes are left. So, let us revisit this part again. Now, how it can be used, these values, to compute your T0, T3 and all those things and all those values when it is there. So, how it will be a more superior than sine triangle PWM. What happened in case of the sine triangle PWM, essentially your switching does not have a sequence. Please see that what we have done here, I can go back to this figure. You can see there, this is a 1 bit change. So, from so what happened, one switch goes on 0 0 1, 1, we are not going for 1 1 0, we have a control and thus we make it 1 0 0. But this kind of control in case of the PWM, it is difficult because it will be turning on depending on whether this modulation index is more than the carrier wave. If carrier wave is less than this modulating wave, that is fine. Otherwise, if a modulating wave is more than the carrier wave, it is going to turn on and it will not consider whether it is a 1 bit change or a 2 bit change, but you can ensure that there is a only 1 bit change to generate any reference. So, it is 1 1 0, thereafter it will be 1 0 0, thereafter it will be 1 1 0, thereafter it will be 1 1 1. So, in that way you can reduce the switching losses also by this technique, and also you can control the duration of it. I shall come later. So, how much duration it will be turning on and all. So, thus you can have a control, and something it is required to have this control for minimizing the losses. And also what happened, since you are exactly, so you have converted this frame. So, what happened here, you have 3 phase voltages, you have converted to the alpha beta frame, then you go to the polar form and ultimately you have exactly calculated the voltage. So, what happened there, you essentially you try to mimic this voltage by the space vector. So, till of course, you apply this and you apply this to generate this voltage for this duration and this duration. And since you cannot, ultimately it averages out and this fills up by the harmonics. And for this reason, it is not a scope of work here. We generally prefer this, this 3 level or the multi-level inverter, so that it can have a more number of space vector to generate a particular voltage, and thus it will be a more accurate to generate that voltage. Thank you for your attention. I shall continue the discussion in the PWM technique in our next class.